Welcome to Iron Beetle, a Twitch show, and a YouTube show as well, where we look inside Beetle, this exciting new database for financial accounting. Let's get started. Okay, so we've been discussing for the past handful of episodes how the Beetle storage engine works. So remember, Beetle is like roughly three things. There is consensus, which is about multiple Beetle replicas running on different computers and communication with each other to process the same set of financial transfers. Then there is the state machine, which is the actual business logic for double entry accounting. And finally, there is storage. The task of storage is to, save information about the accounts and transfers in a durable way and in a way that scales beyond just the amount of available random access memory. Inside the storage, the core data structure is the log-structured merge tree. So for during the last episode and during the episode before that, we looked at the static snapshot of this data structure. So logically, log-structured merge tree stores just a sorted set of items. Internally, this tree is organized as a collection of layers. And when you do lookup, you progressively look up in the first layer, in the second layer, in the third layer, and until the end. But the first layer, which contains your item, gives you the result. That is, items in upper layer shadow, obscure, occlude items in the layers below them. A single layer contains a bunch of tables, and a table consists of blocks. There is the data block, which contains pointers to variable blocks, and there are variable blocks. And the variable block is just a simple array of items. So, bottom line is that we compose a large, logically contiguous sorted array of items by aggregating many individual arrays together. So, two things we haven't covered just yet. First is how exactly this tree evolves over time. How we add new values to this tree, how we remove values from the tree. And the second bit, and the topic of today's episode, is how exactly this tree ends up written to and read from the disk. So let's dive right in. Okay, this is our Ironville source code. As usual, the source code is on GitHub. I'm looking at specifically the Iron Beetle branch because I don't want the branch to change a lot between different episodes. But sometimes I do update the branch. So, to make this discussion about trees and blocks more concise, we had this schema which describes how physically each table is represented. And the physical representation of the data block is just the set of values, and physical representation of the index block is the set of addresses of value blocks plus the minimum and maximum keys of the corresponding data blocks, so that you can first binary search in the index block and then binary search in the data block. And I have repeated this word block many times. This is because like the atomic unit of our storage is a block. If you go in this constants file, you see that we have constant which is called block size. And that means that like all our blocks are exactly the same size. Basically, we just, cut the disk into neat little squares and use these neat little squares to store all the data. I think the size of a square is 0.5 megabyte. The data structure, which organizes the block in this set of squares, is called the grid. And this is the subject of today's episode. We will be looking at how the grid works. So again, conceptually, the job of the grid is extremely simple. It should, given the address of a block, read the block from disk, or given an address of a block, write the block to disk. But again, as usual, details are slightly more interesting. Important thing to note, kind of like conceptually, is that kind of like this grid is a universal substrate. So everything else we have in storage is built on top of the grid. And in particular, as we've just seen, LSM trees function by using grid blocks. Okay, so where the grid is exactly situated on disk. This is described into this zone data structure. TigerBeetle, by design, only has a single file. So there is just like, 0_0.TigerBeetle, which stores the entire state of a single replica. We don't rely on a file system, and even for the single file, we use direct input-output. So this file is separated in several zones. Superblock is something we'll be covering sometime soon. While headers and while prepares is something we've actually covered when we were discussing consensus. This is our like right ahead log. Then client replies, something we didn't talk about yet, but well, basically some auxiliary data structure. And finally the grid. All these first zones are fixed in size. So you see, like, there's size of superblock, size of header, size of prepare, size of client replies, blah, 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 blah. There is no size of a grid because the grid actually is unbounded. So our data file can grow to be arbitrarily large. And that's why the grid is just the last part of the data file. So data file as a whole consists of a fixed size header plus a variable sized flexible grid which grows. So internally, grid is subdivided into blocks of fixed size, and whenever we are talking about the block, we also make sure that the in-memory memory used to represent the block is also aligned by the sector size. Because, well, first of all, that might remove some resonances because, if the disk internally has some page and structure, if you align it to, well, no, actually. Okay, so this I'm talking nonsense because, again, the alignment of your slice of bytes memory has no bearing on the location of this slice of bytes on disk, although on disk is also going to be aligned. But what you need the memory alignment for, I think, is that the underlying Direct.io API in Linux actually requires that the in-memory buffers are aligned. The question in chat, is the Direct.io storage done using IO ring? So yes, we do all our storage through IO ring, and I think we even looked at this in one of the previous episodes. So like the underlying, so Grid is disk access based on blocks. And underneath the Grid, there is storage. Storage is raw access, which says just given this offset on disk, like read me this amount of bytes. So it doesn't know anything about the blocks. And underneath the storage data structure is just this IO Uring data structure, which we also looked at it before. So yeah, you see, just IO ring. And while we are here, let's see where we are doing IO direct. Okay, FB supports direct IO. Yeah, you see, here we request that we want direct IO, that we want to bypass any kind of kernel caches. And it's an interesting story why we want to do that, but I will probably leave that for the next time. But like the short story is that page cache of a operating system doesn't have a very good error reporting. Basically, like you might write data to disk, and your write might fail, so the data doesn't hit the disk, or like it tries to hit the disk after fsync, but well, something went wrong. But it still remains in the page cache, and you get cache coherency problems between what your cache says and what you actually have on disk, and these coherency problems might persist even across restarts of your database, and that kind of like makes really hard to make sure that you do have something durably persistent on disk. That's why we like just bypass the kernel cache altogether and do direct. Anyway, let's go back to our Grid and just looks how it works. And let's start with write path. So write block. This is like the basic operation. As usual, this is input-output, so this is asynchronous, and because we use Zeek, we represent asynchronous operation as just functions which takes callback. Then we pass the actual block, and here, okay, so this strips everyone. So block pointer is a pointer to a block. Well, that's obvious. And star block pointer, well, is a double pointer. And the reason for that we'll probably cover later today. It has to do with caching. I'm not sure that that's like necessarily the best design, but basically Grid can replace this particular region of memory with some other region of memory which it takes from the cache. Okay, so let's go and see how the write path works. Okay, Okay, I forgot to cover two arguments here before that. Well, as usual, we have Grid.Write, which is some data structure allocated by the caller, which stores all the state required to execute the read. Because again, remember, target doesn't allocate memory. And that makes asynchronous programming somewhat tricky. Because, well, if you think about asynchronous operation, it has some kind of context, like, well, what are you even doing? And because this operation is asynchronous, this context has to live somewhere while the operation is in progress. And the way this is typically solved is that, well, this context just, allocated on the heap and deallocated when the operation completes. But you cannot do this if you don't allocate memory dynamically. That's why for target any kind of asynchronous programming in target requires that the caller statically allocates these kind of like environments for closures of asynchronous callbacks and passes them explicitly. So that's okay. This is super handy, but so let's just like take a look who uses Grid.Write. Okay, yeah. Compaction will use Grid.Write. So, okay, this is running far ahead, but well, the structure which will actually mutate our LSM tree on disk is going to be called compaction. So in this compaction, we have two read operations and two write operations. And whenever compaction needs to write block to disk, it will pass this pointer to this block right into the grid. And then that's how we get this write pointer. And well, the grid can use that to store all the information about the in-progress operation, and it doesn't have to memory manage it because well, this thing is managed by the caller. This is very extremely common pattern in target. Okay, I see another question in the chat. Does development of target requires a deep understanding of Linux kernel APIs? And if so, could you give us a commonly implemented API called by target so I can go through them through docs? Okay, so I would say that no. We actually don't need a deep understanding of the Linux kernel API because we intentionally minimize the API surface. We intentionally don't use fancy Linux syscalls. So we are running on top of IO uring because IO uring is the correct primitive to think about asynchronous operation. You don't want to do individual syscalls. You want to say, hey, I want to do this batch of operations, and then you say, I want to say, okay, what operations are completed? And that means that you want to have this LMAX disruptor thingy with ring buffer with concurrent read and write, and that's exactly what IO uring provides you. But we don't actually, depend specifically on some advanced Linux kernel features, we don't use BPF or anything like that. And that's, again, deliberate design decisions because, well, hopefully target will be there for a long time, and, well, maybe one day Linux wouldn't be the primary operating system on the servers, and, well, at that point we should be able to retarget target for something else because, the specifics of the syscalls doesn't matter. The underlying, the overall interface paradigm with batched syscalls is probably going to be implemented in any kind of future successful operating system. Okay, but in terms of where this actually happens, we have this linux.zig file in target, and that basically covers the entire syscall surface we use. And honestly, this is just okay, this is the extent of our knowledge of the kernel. This is the entire set of a syscall that target issues, and it's like super tiny. Accept, close, connect, read, receive, send, timeout, write. That's it. Nothing more. So it's extremely simple, and we are pretty agnostic of the kernel. Okay, coming back to our Grid.Write. The final argument we haven't covered is whether this grid is a repair or whether this creates a new block. I probably won't be talking about this today because this concerns, like, evolution of data over time, and we want to look like mostly on the static. We want to look mostly on the static picture right now. But okay. So how do we write a block? Well, as usual, we do a bunch of assertions, like for example that the header of a block mentions the same cluster that the cluster of a core data file. And again, this is something I've discussed, but bears repeating, that in our consensus, we said that, hey, there is only a single type of messages in Tagabiddle, and like every message starts with this single header. The exact same header is the exact same header is what we use to store blocks on disk. So again, header from block is going to just cast the prefix of a block to the header, and it will have like all the same values, all the checksum of the header, checksum of the body, cluster, epoch, whatever. Okay, so get the header, run some basic assertions. Again, there is like this assertions related to like the lifetime, like the evolution of over time of the storage, like they were like canceling, where we already write in this grid this block whether this block is free, whether this read is coherent, which is again topic for tomorrow. And what I think for us is, well, what we actually do here is that we zero out any pattern. Because for direct I/O, you can only do input-output of the like even number of sectors. So you cannot, like, if you are talking directly to disk, you cannot tell the disk, hey disk, please write this single byte, because like the hardware doesn't operate that way. The hardware requires like a whole contiguous sector of stuff. So that's why if our block happens to be less than a sector, doesn't end on a sector boundary, we need to zero out the rest, because we are going to write the entire sectors. Then we fill out the context for our synchronous operation. Basically, the user supplied callback, the address of a block, the pointer to the block's data, and the checkpoint ID, which again is related to the evolution over time. Finally, we require an input-output operation. And again, this is also kind of like, okay, I'm getting lost here. This is also a common pattern in Tagabiddle. Like Grid wants to be concurrent. We want to write multiple blocks at the same time. But again, because everything is statically allocated, we need some bound on that concurrency, because otherwise we might be running like infinite amount of blocks at the same time, and that will require infinite amount of running, which you cannot deterministically allocate upfront. So for that, we create this IOPS data structure, which is basically just a free list. Parameterized by comp time, maximum number of concurrent operations. Actually, let's look what is this in production config. Grid, oops. Yeah, so we allow, like by default, we allow like 16 concurrent write operations. And inside we store the context for like the underlying storage right. So remember, like this pattern where the caller allocates and stores the right is like recursive, because the grid requires that compaction stores writes, but then grid internally uses storage. So grid also need to have storage right somewhere, but well, it stores it inside like its own right IO. Anyway, so on the write block, we try to allocate a new input-output operation. So if there are less than 16 in flight, then we succeed. Otherwise, well, there are already 16 blocks being written, so we cannot write this block, so we need to queue it up. And for that, we use an intrusive list. So write queue is a linked list of these write data structures. So you see, like, this write data structure contains this next pointer also to the write data structure, which is what this FIFO uses to like arrange them in a linked list. And let's just see. So this is the place where we say, okay, if there is no available write, let's enqueue this. And let's see the opposite where we pop it. Okay, and this is, so this is enqueuing. And this is where we completed some write of a different block. At the end, we say, okay, so if we actually have some write queued, let's try to, again, write the thing. Okay, but if we successfully allocated the IOP, then we are going to go and start writing this block. And it's interesting that after we like complete it and go back to enqueued writes, then we actually reuse the same input-output operation because, well, we don't need to acquire a new one. We can reuse as well. Okay, there is, I see there is another question in the chat. What's the most ideal hardware stack for Tagabidal, and how do Tagabidal guarantee deterministic behavior on hardware? So yeah, we only support production deployment on Linux, but we actually don't require like much that. We do need a fairly modern CPU to support some advanced cryptography we use for our checksum. But other than that, yeah, kind of like basically like whatever. Other than that, like yeah, basically more RAM, faster disk, fast networking, faster single core CPU performance is what makes Tagabidal runs faster. More cores does not help Tagabidal because, well, we are single threaded. And the second part of the question, how Tagabidal guarantee deterministic behavior on hardware? Well, we don't guarantee deterministic behavior on the hardware. Like hardware like behaves in a non-deterministic way. And for example, here you see the grid supports concurrent write iteration, and if you like issue 16 operations at the same time, well, who knows which one finishes first. What Tagabidal guarantees, though, is that regardless of the order of operations, regardless of the order of completion of operations, the result is going to be exactly the same. This is actually one very interesting property which we'll be discussing well, sometimes, that the actual data file is going to be like quote identical between different replicas. Well, okay, of course, because this is distributed system, and replicas generally have like different sets of information. So kind of like there might be parts of data file which exist on one replica but not on the other. But if a particular block is allocated on two replicas, is not free on two replicas, that block is going to be exactly the same. So that is the determinism that we provide. Okay, another interesting question. Okay, So many questions. I really love it. But please, thanks for asking in the chat, because well, if you have any question, then probably someone else also has the same question, and they're just too shy to ask. And it's just helpful to discuss specifically what is interesting. How and when is the grid queue allocated? This is a brilliant question. So this is like really it. It's like, you know, when I joined the trial beta, like on the very first day, this was like exactly the question I was wondering about, like, where is the queue? Because like I join and Tagebital like doesn't allocate memory. This is cool. Like I know how to do it. Like you just don't allocate memory, and that's it. And then I was like looking at some IO ring code, and I was looking, okay, so this is asynchronous. And then I was, well, wait, but that doesn't add up. Like, okay, if you're asynchronous and you like schedule more synchronous operations, then well, you need to you gotta queue them somewhere. So you gotta allocate that queue, and like that queue is going to be fixed in size, and that queue is like, you know, like going to overflow. And what if you're like wanted to schedule a new asynchronous operation, and that operation like, you know, overflows the queue? Like, do you allocate? Well, you don't allocate, but then like you just drop a separation on the floor, but like, you know, you cannot just drop a separation on the floor. So how does it work? So the key idea here is the queue is intrusive. This is an intrusive linked list. So let's look for this carefully. Okay, so okay, Grid.Write. Do we have anywhere like an array of those? Well, actually, okay, yeah, that's it. So this is replica. The replica sometimes needs to write blocks to grid. I think this mostly happens like during repair. This replica internally stores essentially an array of block writes. So if you look inside these IOPS, then it stores, yeah, just an array of items. So when we create replica, we just allocate this constant time, comp time array of block writes. And inside this block write, there is a grid write. So the picture, let me actually, oh dear, new window. Yeah, because I think this will help if I display this. Okay, so we have our grid. Well, it is grid, that's why it is rectangular. Then we have a replica. And a replica internally actually, let me replica. A replica internally allocates an array of writes. So this is, let's just call it W, like write. And anything here is a separate write. Now, inside a single write, there is actually a pointer a field which is a pointer to the next write. So at the start, I think all those pointers are just null, like, you know. I think I have drawn too many grid writes. And then inside this grid, there is this FIFO structure. Write queue. And the FIFO internally stores like a pointer to write block. So inside the grid there is like this pointer, and that initially also points to null. So this all those pointers like right now point to null. And then let's say was there extra other point at k? Okay. Okay. Let's say I take like this write and try to move it to the grid. And let's say that the grid actually like cannot process this write because something other than replica occupied all writes. Well, what do we do here? Well, in this case, we redirect this pointer in the grid to point to this write. And if we then try to add this pointer to the grid as well, and we also cannot do this, what we will do is that we will, okay, this is horribly complicated. So, okay, we had this picture, yes? A grid points to this write, and this writes point to null. Then we say, okay, now we want to add this write. We'll make this write point here, and we will redirect this pointer to point to this write. Okay, and now you have like this, like, you know, a linked list of the two things, and that's that is how your queue is formed. So the cool thing here is that replica is not the only thing in our code base which allocates writes. So there is also, like, you know, there is like this smaller thing. Okay. Called compaction. So this one is going to be compaction. And compaction also is going to store the exactly same writes. So again, in terms of code, okay, I mean, I'm not sure if it's a good idea to try to show them all side by side, but let's try. Okay, that's too small. Okay, this is bearable. So this is replica, and replica has writes. So this grid repair writes here is exactly this thing here. And then in addition to replica, we have compaction. And compaction stores writes here. So this is replica here. This is compaction here. The cool thing here is that if now compaction, okay, I'm pointing with my finger, but obviously that doesn't work. If now compaction tries to, like, you know, take this write and go to the grid, and the grid says, okay, this doesn't work again, then what will be happening is that we'll go and change this pointer, the point here, and then this thing here starts to point there. So you see, this is brilliant. We get a linked list of write operations, and this linked list is statically allocated because, well, the replica allocated just an array of writes, and compaction allocated just 2 writes as fields. This linked list is like fixed size, and it spans across multiple data structures. So neither replica nor compaction don't really know about each other directly, and yet the grid, by managing someone else's memory, manages to create these unified linked list of operations. So let's actually take a closer look here. So in the write block, no, not replica, grid. Right above me. If we don't have an IOP, we push this write queue. And this is FIFO push. And we just go and say, okay, if we already have some element we are pointing to, then we now say that the element we are pointing to now points to this new element, and this new element is, well, the new element we are pointing to. And that's basically how it works to pop the element, we use the second pointer we have here. I must say, right now I'm a little bit confused about the specific semantics of in and out pointer. So it's first in, first out. That means that out points to the first element, then first element points to the next. So kind of I guess what you have here is that you have linked list like this. And then you have in pointer pointing to this element. So this is in. And then you have out pointer pointing to this element. Out. So when you want to... I should have created something separate for this picture. Let's move it here. And now replica moves back. So this is the FIFO. When you push element to a FIFO, you put a new element here, you change this pointer here, and you override this in pointer. When you want to pop from the FIFO, you advance this pointer. Advance this pointer. I want to advance this pointer, and you just redirect this one to point to null, and that's your FIFO. And again, the reason why it works is because all those square boxes, all those individual elements, are actually pinned in memory and never move. That's why you can have pointers between them and don't worry about pointer invalidation, and you don't need to make this queue own the elements. Hopefully this makes it a little bit more clearer where the queue is allocated. So the full answer here is yes, this is the queue. There is a queue. The queue has an implicit bound. There is no code in Target which says, let's create a queue of at most 1,000 elements. No, the bound is implicit because there is only a finite number of elements that can be in the queue. So there's a queue of writes, and there is only a finite amount of writes allocated. Because some data structure, every data structure allocates some amount of writes once, but in some array, but they're there. And the queue is formed by changing the links between those writes. So the maximum length of the queue is the total number of writes you have. But this total number is not coordinated across the entire code base. It is genuinely appears as a sum of individual writes in every data structure. Okay, hopefully you are not completely confused. So yeah, I think there's like a bunch of different questions there, but I think okay, yeah, okay. Thank you for this. Thank you for the comment that says that like okay, it makes sense now. Yeah, this okay, this is hopefully helpful. Yeah. We essentially do have like this like queue ring of writes. Okay, so let's get back to actually look at how we like write data to disk, because again, and don't worry if you don't get this entirely, because this pattern like repeats throughout Terminal, and we'll be probably discussing it a couple of times more. And we actually already discussed it when we were looking at the storage, when we were looking at the I/O. So in our lecture about I/O ring, we had exactly the same thing with completion, which stores a pointer to a next completion, and which is stored in this intrusive linked list. So in I/O ring, the underlying ring buffer in kernel is fixed size. So when we try to submit new syscalls, we might run out of space in the kernel side of ring buffer if some of our syscalls are very slow to complete. But no worries, we just enqueue all these operations in user space using this intrusive linked list. Okay, going back to Grid. Right. So how do we actually write block? Let's go to heavy path. Okay, so we are here. We have a group. We have our write IO, which contains a write from the storage, which internally contains this completion from IO ring, which we've just looked at, and we have a write. And a write is basically information what exactly we are writing. The address of a block and the actual content of a block and the checkpoint. And the checkpoint is going to be related to these changes over time. Okay, so we then fill these IOP fields. And then we ask the storage, then please write data to disk. Which data? Well, the block we have. And again, blocks are fixed size, so they are always half a megabyte. But actually, block might be only partially filled. And for a partially filled block, we like do partial writes. So we round up the size of a block to the header, and we already zeroed this suffix before, so we know it's 0. And we ask to please write this thing. And then we compute the block offset from the address of the block. And again, like I really love TinyBittle because the code is so simple. So what is the address of a block? Well, it is what is the offset of a block? Well, it is block address, which is just the number of a block, multiplied by block size, that constant. And for completeness, let's quickly look at how write sectors works. Write sectors calls the underlying write operation using this buffer and using the offset of storage. And the offset in storage is, we get it by adding the offset within a zone, so within a grid, to the offset of the zone itself, like the offset of the grid itself. So for us, again, this zone is what we've been looking at the very beginning. This zone for us is a grid. So the zone offset is going to be just the sum of sizes of all the other zones. And then we just go and write. Just go and write. Just go and write at that offset that data. When the write completes, okay. So I was. Okay, yeah. It's actually interesting. So it might be the case that we are not able to write the entire buffer in just one syscall. So on the right, we actually look at the number of bytes written, and if we are not done, then we write again whatever is left. Okay, let's move on. So we ask the storage to write a block. After it is done, it invokes a callback. Again, as usual, Zeek is an language without closures, so there is always a bit of a legwork to get from a callback to the context. So the callback accepts storage write, and it's actually very helpful because we see the code which calls the callback right here. So the callback invokes the storage write. The storage write is embedded in our write IO. So we ask Zeek, hey, Zeek, this is a pointer to storage write, give me the pointer to completion. Then we get to IO. And then we get back the grid itself. Because when we started the operation, in this IOP, we store the pointer to ourselves. So this is again, if you are a Rust programmer, this will make you cry because it's all kinds of crazy aliasing pointers to itself. But well, it works in Zeek. Okay, so you get back pointer to the grid, and finally you could do something interesting here. Okay, so first of all, we insert the block into the cache, and then okay, this is okay, this is that crazily confusing things why we use pointers to block rather than just pointers to block. So after we completed the grid, after we completed the write, we take a cached block and we swap the pointer to the block which we asked to write with this new cached block. So caller, okay, so caller asks us to write a block. It gives us a pointer to a block. We write a block to the storage. Then we store, we don't immediately erase the in-memory data. We store a pointer to that block in our cache. And that creates a problem because, well, the caller still has, the caller still has access to this block. And now this block is also in the cache. So if, for example, the caller starts to mutate with data, the cache is going to get busted. So what we do is that we now actually swap pointers and we give out a fresh block to the caller. So that so in other words, when the caller asks to write a block, after the write is complete, the caller's block gets replaced with a fresh empty one. so that, again, like because there is no memory allocation, you cannot actually delete and create blocks. Like you need to always maintain these physical law of equality, that the number of blocks never increases nor decreases. So if you write one block and that block is gone, you need to get some block in return, and that block is going to be empty. Okay, and then we did this little substitution dance. Then we go back to whether we have write queues, any write queued, and if we had a write queued, we pop that write from that intrusive linked list, and we schedule another write. If we don't have writes, then we can release our IOP, which means that, again, so we have IOPS, which is an array, and we have a FIFO, which is an intrusive linked list. So we release our IOP to our IOPS array, which just sets it back into the array and makes this IOP available for any further writes. And then we call the user supplied callback. So this is like a lot of code, a lot of words, but let me try to summarize. So input-output happens on the granularity of blocks. Each block is identified by its address. When you write a block, you say given this block, pointer to this block, and given this address, so the address is filled by the caller, please make sure that the corresponding block on disk contains this data. Internally, Grid manages concurrency. A Grid can write several blocks concurrently, but well, it might be the case when someone tries to write a block, the Grid is already writing the maximum allowed number of blocks. In that case, the Grid will enqueue the block in progress into a linked list of blocks. So the overall flow is that, okay, there is a write request. I'm going to acquire a write operation for the line storage. If I am not successful, I'm going to enqueue my write. If I'm successful and I have a write operation for a storage, then I schedule the actual syscall to transfer data to disk. After that syscall completes, before I return to the caller, I see if I have any other writes enqueued. If that is true, then I reuse my input-output operation to do that queued write. If it is not true, if there is no more work to do, then I return my write IOP to the pool of free write IOPS. And finally, I invoke the user's callback. Where exactly the data for a block number n gets to disk? Well, it is a fixed offset from the start of the data file plus the block address multiplied by the size of the block, which is just half a megabyte. And that's it. Okay, I kind of wanted to cover the read side of the Grid as well, but we are sadly running out of time, and the read is actually longer than write, so I'm not going to tell it today. So I'm just going to read it on a cliffhanger, and the cliffhanger is that written from the Grid cannot fail. So the API is structured that way. Actually, let me look at, I don't know, compaction. Okay, so if you see, for example, how compaction read blocks, well, it reads blocks, and then there is a callback, and well, the callback just, goes and uses this block as if it is always valid. So there is no error handling here. Like there is no like code like if read was an error, like retry or something like that. So how is this possible? This is a quiz, and I will ask you the next time. How is it possible that table claims that it not only correctly deals with errors, it actually anticipates that the disk might fail, that the disk might return bogus data, and promises to maintain data durability even if disk is like almost completely broken. And at the same time, when you like open Trackcapital's code and look at how it reads block from a grid, you see that there is no error handling. That the code simply does not, like, have any possibility for the underlying syscall to fail. Like there is no error code here. Like there's just like read block, and we just like go and start using this data. Okay, and if you would like to know the answer to that question, well, then please join me exactly 1 week minus 1 hour later at 5 p.m. UTC on Thursday on Twitch. I see you then, and thanks for joining with me today.